Right. Hello, everyone. Welcome to today's recitation, which is going to be on attention. Can everyone see my slides?
Looks good, yeah.
All right, awesome. So today's slides are courtesy of last semester's DAs Jingwei and Bharat, who put together a really good slide deck, which I'll be using again today. So let's get started with attention. So far we've looked at how RNNs work, and we've used RNNs for various tasks, and you'll also be using them in homework 3P2 for the problem of converting a sequence of speech frames to the corresponding phoneme sequence. And you might remember from lecture that this problem has order correspondence, but not time correspondence. Some other tasks that RNNs can be used for include translating text from one language to another. For example, on this slide, we have the sentence, "I like cats more than dogs" in English being translated to Japanese. Some other things that can be done using RNNs are things such as, given an image, come up with a caption for that image, or given a pair of question and document, select the correct span of the answer from that given document. And these tasks are generative in nature, meaning that the output itself is a sequence which is generated from the input, and the output is dependent on the entire input sequence. So you have to have seen the entire input sequence to be able to generate some output. And more concretely, this is called conditional generation, where each term in the output sequence is conditioned on the entire input sequence, shown in green here, x1 to xt, where you have t timestamps in the input, and all the timestamps of the output until that output timestamp. For deep learning applications specifically, we come up with an encoder-decoder sort of architecture for this, where each of the encoders and decoders are realized as deep neural networks, such as RNNs. And though the encoder and decoder have their own separate parameters, they are trained end-to-end jointly. So the decoder, in order to be able to produce this sequence of output tokens Y, needs to have some kind of encoding of the entire input sequence. And this encoding is assumed to capture the entire meaning of the input sequence and should have access to the past states of itself. So how do we encode the input sequence? Well, we remember that RNNs and LSTMs and GRUs spit out these vectors called the hidden states. And these hidden states encode information about not only that particular timestamp, but of all previous timestamps as well. So we assume that the last hidden state from the last input token will have effectively encoded the information from the entire input sequence so far. And now that we have this representation of the entire input sequence, how do we tell the decoder how to use it effectively? We have two options. We can either pass in this hidden state from the encoder to the first hidden state of the decoder as the first hidden state of the decoder, or we can repeatedly pass this encoding to the output network at every time step. But as you can imagine, there are some challenges while doing this. First, it's hard to train. A single input encoding vector, having all the information from the input is difficult to achieve, and earlier inputs might get forgotten in this process. It's also hard for the decoder to focus if you're giving it the same thing repeatedly at every time step. And so there is a need to come up with a more flexible input encoding, which is determined by that particular step of the decoder. For example, if we look at a translation example from English to, say, German, if the input sentence is, I eat an apple, for example, and you're translating that to German, it's unlikely that you're going to look at all the words at every time step. For example, if I want to translate only I into German, then it's not really useful to pay attention to the other words in the input, such as eat and apple. And so we need a more flexible encoding type, which can dynamically look at different parts of the input. So that's basically the intuition of attention, that at each time step, the decoder focuses on a specific segment of the input to produce the current output. And more specifically, we let the network learn how to focus on the input segments. And this is done in the same way that we've been training neural networks so far through backpropagation. So the concrete formulation is such that this input encoding, which you feed into every time step of the decoder, has to be a function of the decoder hidden state itself and the encoder hidden states at each time step from the input, and not only the last input. So the general attention mechanism is such. You construct a query called QI from the decoder hidden state. You construct a key and a value from the encoder hidden states, and you calculate some attention score. So for now, let's just assume that attention is some function, some similarity function that gives you a score between the query Q and the key J. And this is going to tell us how much attention or how much focus we should give to the jth input term at the ith output stage. Once we have all the attention scores for each of the input tokens, we can then construct a weighted sum of the values of these inputs by multiplying these attention scores with the corresponding values, and finally feeding in that new representation into the decoder state. So one of the variations of this general mechanism is the dot product attention, where the attention score is calculated as a softmax over the dot product between the query Q and all the keys K. Another variation is something called bilinear attention, and this is when your queries and your keys and values are not in the same vector space, so they have, say, different vector dimensions. Then you can introduce another parameter matrix W between the queries and the queues to make sure they're all in the same space before you compute the dot product attention. But I think it might be useful to visualize these operations a little bit clearly. So I'm going to switch to my iPad now. All right, can you guys see the iPad screen?
Yep.
Yep.
All right, awesome. So in keeping with the same notation that the slides follow, the blue is the encoder and the orange is the decoder, and your input sequence is I eat an apple, and the corresponding German output is Ich esse ein Apfel. And this is your typical encoder-decoder without attention. You're taking the last hidden state from the encoder, which is H3, and feeding it to start off the decoder, feeding it as the hidden state of the first time step of the decoder. So how do you compute the keys and the values from this? When we say construct keys and values from encoder hidden states, we basically mean that for each of those hidden states, you project them into the keys and values using new parameter matrices called WK and WV. So now you've essentially ended up with a set of key vectors and value vectors for each of those hidden states. Similarly, for the decoder, you take the hidden state of the decoder, and pass it through a different parameter matrix, WQ, which gives you a query vector. And even though I've shown all 4 timestamps here, typically you only do it one at a time because H1 is going to be dependent on H0, H2 on H0, and H1, and so on. So that's something to keep in mind, but just for the sake of convenience, I've shown all 4 queries being generated currently. Well, what next? Now you compute the attention score. So you take the query Q and you multiply it with the entire key matrix and take a softmax after that, which gives you the attention scores. When we say scale the values by the attention scores, we mean simply multiply those attention scores with the corresponding value vectors and sum them all together to get this final representation. And this final representation is only for one decoder state, since we used only Q0 at the top to come up with the attention scores and the representation. And finally, you feed in that representation in red into your decoder state at the corresponding timestamp. And this is what the complete picture looks like, almost complete. I didn't draw out all the queries and keys and vectors because it would have become a little more messy. But this is what your general attention pipeline is going to look like. Right. Let's go back to the slides. All right. I guess you guys can see my slides again. So another version of attention is additive attention, where instead of taking a dot product between the queries and the keys, you first project them into a common space and then sum over them, take a tanh, multiply that again with a different parameter matrix, and take a softmax over all the J input tokens. This is another variation of attention called scaled dot product attention. And I think this was introduced in the paper called Attention is All You Need. And the difference here is that similar to what we saw on the iPad diagrams, you generate the queries, keys, and values by passing the hidden states through separate MLPs. Instead of having only a single weight matrix, you can have an entire MLP to pass through. And another difference is that the dot product in the softmax is scaled by a factor of 1 over the square root of the hidden dimension. And the authors justify the use of the scaled dot product by saying that this is in order to normalize the dot product so that when the hidden dimensions get too large, the softmax isn't pushed into regions where the gradients become too small to propagate back. And they compare, in the paper, they compare this with additive attention, and they find that it performs just as well, if not better, I believe. So this is great, and this will already help us generate outputs which are a lot better than simple encoder-decoder architectures, but there's still a few problems with simple RNN-based attention. And that mainly stems from the sequential natures of RNNs, which makes them quite difficult and almost impossible to fully parallelize on GPUs. There's still a step-by-step left-to-right computation where the output is always dependent on the previous time steps. And so you cannot leverage the full power of GPUs. They also struggle with long-term dependencies. And even if you use LSTMs, you still cannot hold all the information across very long input sequences. Also, another use case is that in NLP tasks, the same word may have different meanings based on different contexts. So how do you deal with these problems? This is where transformers come into play. Again, in the paper, attention is all you need. The authors proposed a revolutionary architecture called transformer networks. And in this paper, instead of using RNNs to do sequential computation, you do something called self-attention, which is basically computing the queries, keys, and the values from just the encoder. And doing that allows you to compute attention scores in parallel across all the queries, all the keys, and all the values in the input itself. And this allows the encoder and the decoder to see the entire sequence all at once. And since there is no particular left to right dependency, you can leverage parallelism to a much greater extent. So to clarify this architecture a little more, we'll talk about multi-head attention. And multi-head attention is just, I believe, a fancy name for having multiple key, query, and value parameter matrices. So if you look at the diagram on the far right, you have the keys, values, and queries which are produced from the hidden state of the encoder as usual. And instead of having one parameter matrix, you have something like 8 or 16 or even more parameter matrices to come up with more keys and queries and values for a single encoder state. And on the diagram on the left is the sequence of operations that the paper proposes to use. So as we saw before, you do a scale dot product attention between the query and the key in the query. You optionally mask it out. So we'll look at the purpose of the mask, which comes into play in the decoder in just a second. But after that, you can do a softmax and multiply it with the value as usual. And the intuition for using multiple attention heads is that each of these heads can focus on different parts of the sequence. And each of these heads can have keys, queries, and values that lie in different vector spaces. So this is what a complete transformer encoder looks like. It contains.
I have a small question.
Yes, go ahead.
So in the last slide, for the multi-head attention, there's a concat block. So does that mean flatten?
I wouldn't say it means flattening. It's just that when you compute, so from the diagram, if you remember that we had those red representations coming out of our final attention state, and you'll have H number of those coming out now, since you have H attention heads. And so you simply concatenate them end to end. And again, project them through a different linear matrix to project it into the vector dimension that you want at the end.
So when you do concatenation, it's still a two. So it will be a 2D matrix.
It will be a vector, I believe, for a single example. Yeah.
Okay, got it.
Mm-hmm. Because each of those attention heads is giving you one vector representation, and then you concatenate all of those. Right. So the transformer encoder contains multiple blocks in the paper. They use 6 of these blocks, which are visualized on the right. And the way the sequence of operations happens in this is that, let's just talk about the gray box at the top for now. You get some hidden states as inputs. As we saw before, you compute multi-head attention. And then there's a skip connection around multi-head attention into the add and norm layer. And this add and norm layer is a layer normalization of the sum of these inputs and the output of multi-head attention. Similarly, there's a second sublayer, which is the feed-forward layer, where you take the output of the first add and norm, simply feed forward through an MLP, and compute another add and norm with another skip layer, skip connection. And you repeat this entire computation n times, where n in the paper is 6. So you can do simply this and probably get away with getting decent results. But the authors also propose using positional embeddings, positional encodings. And the intuition for using positional encodings is that now that we've gotten rid of all the left to right computation in our network, how will the network figure out what the relative ordering between each of those input tokens is? And so you come up with something called positional encodings, where you add some value to your input embeddings to let the network learn that there is some inherent order in the input sequence that you're passing it. And one proposed positional encoding is to use a sinusoid. So you can just model a sine wave which goes over all the input sequence tokens and add the values to the traditional word embeddings or input embeddings that you have. Or you can let the model learn its own positional encodings, but there wasn't a big difference in performance from what the authors report. Without positional encodings, the two sentences shown here in the last bullet point would be identical to each other. So I like 11,785 more than 10,707 would be identical to the output for I like 10,707 more than 11,785. Next, we have the transformer decoder. This is almost exactly the same as the encoder, except that you have an extra layer here, sublayer here in the beginning called the masked multi-head attention. And the reason for using a masked multi-head attention instead of normal attention is that for each of the output sequence tokens, you want to enforce some sort of left to right dependency. And so you come up with a mask matrix, which is just a way of blacking out some of the inputs at each of the output states. So for example, let's see, an example would be that you have some sort of a diagonal matrix, which at output state J only pays attention to the previous J-1 input states. And that's the only difference between the transformer decoder and the encoder. The rest of the block looks almost exactly the same. So putting it all together, this is what the entire transformer architecture looks like. The input sequence is used to compute the keys and values in the encoder. Masked attention blocks in the decoder transform the output sequence until the current time step into the queries. And multi-head attention in the decoder combines the keys, queries, and values. And the result is projected into output probabilities for the current time step. So that's the end of my presentation. There's more resources that you can find with these two links, and the slides are already posted on the website. So I'll pause here if you have any questions, and Shruti can then start her part of the presentation.
Do you have any questions?
Can you explain again what is the mask?
Sure. So in the decoder, you want there to be some sort of left-right dependency, especially when you're doing language modeling. And a mask is basically a way of telling the decoder at each step in the output sequence to not pay attention to the consecutive time steps. So for example, if you have 5 time steps in the decoder and you want to calculate attention over all of those 5 time steps, but you're only at the 3rd time step currently, then the mask is basically going to multiply time step 4 and 5 with zeros and only compute attention over time steps 0, 1, and 2. Does that make sense?
Yeah, so actually it is going to sort of like sort of obscure the outputs that it's not supposed to look at yet, right?
Hmm.
Okay.
Correct.
Thanks.
Any more questions before I start my presentation?
I have one question. So the last diagram you showed, putting it all together. So that only does that only work for a single embedding, or does it work for the whole sentence? And you just slide the embeddings over.
It's for the entire sequence. Let me share my screen again. So it's going to take one entire sequence of input embeddings. So your entire sentence will have some matrix of input embeddings that's fed into multi-head attention.
Right. So would the input embedding contain the entire sentence, or would it be one by one, but sequentially fed into it?
The entire sequence. So for example, if you have 5 words and each word is 300 dimensional word-to-vec embedding, then the input to this entire architecture will be 5 by 300.
Got it. Got
A
it.
matrix of 5 cross 300.
Got it. So if the sentences are of different lengths, we have to pad it all to the
Correct.
same length.
Yeah.
Thank you.
No problem.
Anurag already gave you information about what attention is and why do we use attention. Now, next important question is how do we use attention? So now let's try to, so before that, I just wanted to give this information that like this example is just for demonstration. You might not be using the same hyperparameters or the same architecture for your upcoming homeworks. So let's start with a toy example. So we know that attention, basically the task is to do a sequence to sequence modeling. And what right in this example, what we are doing currently is that we are going from an English a representation to its corresponding pronunciation, like a word to its corresponding pronunciation. So let's take an example. So for example, we have a data which says C, and we see its corresponding phoneme representation is S, like whatever this character is, E. So we have like 12 examples in which every word has its corresponding phoneme representation. Then we have like a set of phonemes that we will be using in our example. For this example, we are using these this S and this slash S represents the start of a line and end of a line, basically start of a sentence or end of a sentence. And this is basically your dictionary mapping or the mapping that you have for all the phonemes present in your training example. Now, so every target sequence would be appended, prepended and appended with start of sentence and end of sentence character. This is basically used for your encoding and decoding purposes. So for example, in your encoding, you use the part which only has start of sentence, and in the decoding part, you only, in the encoding part, you only have start of end of sentence, but in the uh, decoding part, you have start of sentence. How will that be used? We'll get to that. So you have your data, and now you want to you have to pre-process it to make it usable in the form of encoder-decoder architecture. So what you do is that if you see here in the example, what could you observe about the phoneme representation? Do you have any answers on that? Uh, like, do you see, is there certain length, like is there a fixed length consistency in the length of the input and the output? No, right? I mean, you see it's SEE, but it's just 2-character representation here. And it varies around all the training examples that we have. So what we do in here as part of pre-processing is that we take, first of all, what we do is that whatever we had in our dictionary phoneme mapping, we map everything as our X representation. So for example, this one, yeah. So I didn't talk about this. So this letters will also represent the index mapping. Um, for example, let's take this C, and we see that in here, S has an index of 3, E has an index of 0 and 0. So your X vector would be representing something like this: 3, 0, and 0. And when you go for your Y vector, which is basically your target vector, which is this phoneme representation, you will again do your index mapping. And if you see example of SE, so when you go there, you get your Y representation to be S, which was 0, and IY, which will be 0, 1, 2, 3, 4, 5. So it will be 5 here, 2 and 5. So so you would also see that as part of your target, you have appended and prepended start of sentence and end of sentence character, which also has an index mapping. So you see here, you have like start of sentence, which is 0. Then you have S, which is 2. Then you have E, which is 5. And then you have like end of sentence, which is 1. So this is how your X and Y would be mapped to the index. Then since you know that like all the character, like all the inputs are not of similar length, so before passing it to the LSTM layer, we will make them of similar length. And that's what we do in here. But before that, we also need our information about what was the input size of each sequence. So we store that information using this. This X length represent the length of each sequence in your training example. And then what we do is that we pass this to your pad sequence, so which basically pads everything to the same shape. So if you see here, 0 is basically your start of sentence representation, 2 is S representation, 5 is your E representation, 1 is your end of sentence representation. But since your maximum the length of your in the length of your input, the maximum length of your input was coming out to be 1, 2, 3, 4, 5, 6. So you had to append 2 extra zeros here. So this is how you make your input length uniform across all the sequences present in that training example. So any questions on this part? Okay. Um, um, Anurag?
Yes.
Yeah, I'm just making sure. Somebody had a question. Do we have to do it manually? Can you speak up and ask? Uh, okay, so yeah. For padding, if you're talking about this part, you can just use pad sequence, which is one of the LSTM libraries, and you can pad it to the maximum length present in your batch. Does that answer your question? I cannot see what's going on chat, so.
I assume it does because there's no response.
Okay, cool. So yeah, so before that, so since we are done with the pre-processing part, now let's see, now let's get into the model architecture. And
There's another question. When exactly are we finding max of X lengths?
Right. So basically, when you do here length of sequence, this is where you take the maximum. So basically, what happens is implicitly you have your length of. So you have already saved each sequence length in x lengths. When you pass this x to your pad sequence, the pad sequence will by itself check what is the maximum length of the sequence passed to it, and then accordingly pad all the input sequences within that batch.
There's another question which asks, is the data transposed as compared to usual? It seems like each data point is represented as a column as opposed to the usual row vectors.
Yes, yes, for this example, yes, that's the case here. So
And another
basically,
question, sorry.
yeah, so I would say why that happened, because you have batch as your second dimension in here. So that is why you see your data as in this way, but you can do anything like what you need, depending upon what kind of LSTM configuration you're using. Yeah.
Right. There's another option that you can pass to that called batch
Mhm.
first equal to true or false, right, Shriti?
Yeah.
Right. Another question is, why are we computing the lengths twice if it happens in that sequence?
So yeah, so this is a very important question, and this I would see how it is being used in the attention model. So basically, you calculate a mask, and this mask depends on what is the input sequence length, original sequence length, because when you back propagate, you only back propagate through those sequences which actually took part in the computation, but not those which were useless, which were like uselessly padded at zero. I'll explain that in the later stages. Yeah. So So now your whole attention sequence to sequence model has three major components. Basically, it has two major components, which is encoder and decoder. But when you want the relative context or the relative sequencing in your like basically when you want your attention to come into picture, you add another component, which is attention component. So we'll see each one of them individually: encoder, attention, and decoder. And if you might have started your homework 3, you would have given a task where you had to given an input sequence, you had to predict the label of it. And for that, you did nothing but like doing an encoding, which was using an LSTM layer. So how would we do that is that we have an encoder, and then first thing that we do is we calculate the embedding of the text. So for the example that we took was C, and we want the corresponding vector representation of that C. We will also provide an embedding size, which is like in your embedding space, what exactly is the dimension that you want for your corresponding input text. So for example, just to make it clear, yeah, so you have like C, and using nn dot embedding, um, in the vector, in the embedding space, you just do a vector representation of this C. So this is what this embedding layer would do. Then yeah, then you pass that particular time series input to your LSTM layer, which would be bidirectional because you want like forward and backward information. And yeah, so these two part will, this is just a simple example of encoding where you have like embedding and LSTM. So what you do is you get, if you see here, we pass the length input here. So first we pass X to our embedding layer. After getting the embedding, we again have to do that back padded sequence thing before passing it to the LSTM layer. And here you pass in your lengths of the vectors. So depending upon this, your sequence will be padded, and whatever padded sequence that you got, you will pass it to your LSTM layer. Now this LSTM layer would give you final state, a hidden state output, your output, and a final hidden state here. Now, using this output, you will pass it to add packed sequences, which will basically do your unpacking, and you will get your encoder input and encoder input lengths, corresponding lengths of each input that you gave, and you just return that particular input. So basically, this particular whole model or whole component would give you an embedding of the entire input. And basically, you do it to reduce the length of your input. You would see that like being used in homework 4. So this is what an encoder does. Um, then we want the information of attention. And for this example, we would demonstrate how dot product attention is being used. So your whole attention has like, when you bring attention into picture, you have like key, value, and query into these three things. And apart from that, you have like so context vector. What each would have, what like each of these mean, we'll explain that. So yeah, so let's go to attention. And before that, I just wanted to explain. I think I would better annotate. Yeah, so
For clarification, we're not allowed to use attention for homework 3, right?
no.
Got it.
So this is your query. This is your whole key value that you get. Um, and what you that you get from the encoder. So what you do is that for each query that you get, you calculate the similarity score with every timestamp of your key vector. And then, for example, this had a value of 0.8, this had a value of 0.9, this had a value of 0.1. So we see that the maximum similarity score of this particular query, which would be a particular timestamp, uh, by query, I mean that when you do your decoding, you will have like start of sentence, and then you have some, for example, IH, and then you have P or something, or N, something like that. And this is what you pass in as your query. And then you calculate the score, similarity score, with your key value, and you get like, for example, you got zero point 0.9 here. So this will be the, so your query will have a maximum score of a maximum similarity score with this, with the entry corresponding to this particular timestamp, which means that it is more related, or your energy is more focused there. And then after you're done doing this, you will convert all this similarity score is what that you got into probability representation. So right now I explained it in zero point 0.8, but the values that you might get might be 10, 100 or something, and you have to convert all of them to a probability representation, which will like bound their values from 0 to 1. And so all your weight vectors, this is nothing but your weight vectors that you get, weight values that you get with each timestamp. And then you do a summation, like you combine all, take an weighted average or a weighted summation, and then you calculate your attention on top of that. So how would that done in code is something like this. Um, yeah, so you have your context and you have your query. Sorry, I meant context when I said key. So so this is your query and this is your context. This torch.bmm is calculating the context and query, the dot product between context and query. And then as we have, like somebody asked that question about why would we keep that length. So, so you have your input sequences, which has like a padding. For example, uh, you had C, and then you have, for example, you have a word sure. So you have like extra two zeros when you do the index mapping, you will have extra 2 zeros in here as part of your LSTM computation, but you don't really need it to backpropagate, or you don't really need it for your attention layer. So what you do is that you keep into account the length of each sequence. So this is your the length of this sequence is 3 and this one is 5. So you want to take into account this information and create your mask, which will only focus on the regions which were really important for your computation. So that's what we do here. We try to create a mask out of that, and whatever which was not important or whatever which was padded as 0 would be kept as infinity. So this is how we create our attention mask. Now I told you that we have like, so this particular, these three things basically computes the similarity score between the context and the query. And after you're done with that, you pass in through a softmax layer to convert it into a probability representation. So at this particular point, you have got everything to be in the value of 0 to 1 for each weight vector, for each entry in the weight vector. And after you are given with the weight vector, then you again compute your weighted average uh, or attention weighted sum, which you use this function again, torch.bmm, and you pass in your attention, which you got in from here, the probability distribution and the context. And this is how what you get as your attention output, which you pass out from your um, attention component of your network. So this is how it is used. Another thing here is how do we use torch.bmm. So I just um, so what the torch.bmm does is that you have your input in this dimension, where first dimension is your B, which is your batch size, N and M. And similarly, you have like the second matrix, which has B, which is your batch size, M and P. So after you apply this function, you have your final output to be N cross P. So whatever is common would be taken into consideration for like doing the matrix multiplication, and whatever the output that you get is in the form of P cross N cross P. So this is basically batch matrix multiplication, and this is how we do it. So this will be becoming very handy in your homework for calculating the attention. And yes, so after we are done with this, then we come to the decoder. So now you have what all information you already have. You have an information where your input was converted to an index mapping, and then you, after doing that index mapping, you passed it to an encoder, and then you also, after passing to an encoder, you also have like how to calculate attention on top of that. Now, so basically we are at the stage where we have like we are passing from text. We have like text as an input, and we want what is the corresponding phoneme representation of that particular input. So that's what decoder would do. You would pass in C, and it will give you a corresponding representation of that word C. So how we do it is that decoder's architecture is a little bit different than what we have done in encoder. So yeah, so if you see that you have like another embedding layer, which will be doing the same thing as we have done in the encoder. Now, after that, another difference point that you need to notice is that we are not using an LSTM layer here. Rather, we are using an LSTM cell. This is so because so if you see the listen, attend, and spell paper, this is what your encoder does, is that it encodes all the information from the input, and then you get your hidden representation in here, and then you use like each particular hidden representation to calculate to like spell it or decode it. And uh, so as part of this, you pass in like so yeah, so you pass in your, so you have, for example, you started with SOS, and this was your query. You calculated attention on top of that, and then you had a hidden representation here. So whatever h0 that you had here, when you're doing it for the second input, you need to have that particular information in here. So which is basically called C1. So this is C1, and then you pass into to the next timestamp. So you cannot do it with LSTM layer, the normal LSTM layer that we use, because you don't have the liberty of passing in the hidden state, like one particular hidden state or the cell state of that to the next timestamp. So that's why we use LSTM cell here. And yeah, so yeah, so if you see in your decoder, you have like LSTM cell, and then you have attention, which will calculate attention, and then you have your final linear scoring layer as we use it in every model. So then how the forward would look like is that you have your X, which is your input, you pass into your embedding layer, then you pass your LSTM, like you have your LSTM for the first particular input, you will have none as your state, but like in the as you proceed through your timestamp, if each previous timestamp would correspond to the state that you have. So then you calculate, use your X and state, and you calculate your new state, and then you use your new state. Yeah, so yeah, so this is your computation of new state, and then you use your new state to calculate the attention with the help of context vector, and you concatenate the attention, the new state, and the X attended, and then you pass into through your output layer. So this is how you calculate, like decode. This is how your decoder looks like. And yeah. So after you're done with decoding, you need to keep all those components together, and you need to start training. And for that, like, let's take this example. You have like your encoder, you initialize your decoder, and you whatever optimizer. So as part of this training loop, you will first call, so you had your input, you will first call your encoder, you'll get a context and a state. And uh, after that, you will, yeah. So after that, you will in here, you will, since you have already got, yeah, like your decoder is already taking into account the attention, it will output your attention, the next hidden state, and the output of the network. And the loss computation that you would basically do is that, since I already told that we want our loss to propagate only through the non-zero values of the vector input vectors that we had, the padded value shouldn't be taken into account. So this, through this active, you're basically creating a mask to calculate losses on those corresponding non-zero inputs. And the by corresponding non-zero inputs, I mean that non-padded inputs, the original inputs. And this is how you calculate the loss for those particular inputs, and then you just do a backward. So this is how we train the network. And after you're done training, then you, so this is not a very good, this was a toy example, so this is not a very good representation of an attention plot. But if you are on the right track, your attention plot would come as to be diagonal. And that's how, like, you I mean, you make sure that your code is running properly, and all your encoding and decoding is happening in the right way. And then, yeah, as part of decoding, there are various different techniques to decode. Uh, One of them is greedy decoding, and another one is beam search. Beam search is gives better performance than greedy decoding, but for demonstration purpose, I'm using greedy decoding. Search would be dealt in class by professor. And so basically what you do is that you have I told you that you have like for every sentence you have start of sentence and end of sentence. So you don't take you make sure that the input that you take doesn't have an end of sentence. You just have your a start of sentence and the corresponding input, and then you pass it through the decoder. And after the output that you got from your decoder, you just take an argmax on that decoder, and that's the probability of the best class that you have for that particular timestamp. And this is what you get. So you just do an argmax that you usually do, but right now you're doing it for every timestamp. And this is how we do greedy decoding. Any questions that you have in the entire architecture? I see some questions.
I have a question.
Yeah,
What is the context?
right. Yeah, so I think yeah, so if you see this diagram, which basically context is the previous hidden state in output that you get. And so what you do is you pass that particular information. So for example, yeah, so yeah, so for example, you started with your SOS and you got some information in here. You pass that context information, which is basically your attention context that you calculated, and you pass it to the next timestamp. So how I would explain that? Again, I can use the paper here to explain that mathematically. Yeah, so if you see that you basically concatenate, so yeah. So here when you see, you have your output here and you have your attention here. So whatever you pass in for your, not here, sorry, encoded input here, and you have your final state here. So whatever encoded input that you have in here, you pass it as, you take it as the context for your first timestamp. So here, so this context is nothing but the output of the encoder layer that you got. Does that make sense?
Yeah, I think so. Thank you.
Hi, I have a question. Do you
Yeah.
train the encoder and decoder together or separately?
We train it together.
Got it.
You have to train them together, right? Because there's no supervision for just the hidden states from your encoder.
Right, because I didn't pay attention to the training code.
Right. Any other questions?
All right, if not, then we'll keep an eye on any questions that might come up on Piazza and post the recording as soon as it becomes available. Shriti, do you have anything more to add?
No, I think that's it. Thank you for coming.
All right, thank you, everyone. Bye.
Thank you.